how to translate the structure into the notation, and how to kind of go back and forth between those two, right? We talked about the key idea here is that hydrogens bound to carbons are understood, okay? And so that doesn't mean they disappear, it doesn't mean they don't influence the shape, it doesn't mean they don't influence the geometry and the electrostatic potentials and the dipoles, and that's not what I'm saying. They don't disappear just because we don't draw them, right? Just because we don't see the air doesn't mean it's not in this room, kind of thing, right? We know it's there, it's understood, they have a purpose, right? But we don't want to draw those in. The other key thing that we learned is that when we do the shorthand notation, we want to represent the structure as close as possible to the actual geometry, right? Without taking 20 minutes to draw a single structure there. All right, so we talked about why we kind of make the bends and the twists and with alkynes where it's linear and all these kind of things with that, right? We talked about lone pairs, which is extremely important. We said that for the most part, we can leave those off, although what you'll end up doing, and what I'll end up doing, is pretty much drawing the lone pairs in, especially when we start to do the reactions themselves, right? Remember, we represent the absence or presence of additional electrons through indicating the formal charge, right? And that's extremely important. That's what we talked about here with this example, you know, how we can change the charge there without actually having to draw in the lone pairs. Sound good? That's a good summary there. All right, that's kind of the basic ideas there of how we represent these structures. Fair? Yeah.
What chapter is this from the book?
Basically, we're in chapters like 2 and 4-ish, or where we're kind of hopping around, and we'll be kind of hitting into chapter 3 here in a little bit, probably at towards the end of this week, but we'll see. Sound good? Everyone with me on that? All right. So we will get started with some prayer then, and then we'll launch into the topic for the day here. So, Lord, we just thank you for this opportunity again, Lord, that we can just come and just learn a little bit about you and the things that you've created, and that we can just glimpse a bit into the creation that you made for us, Lord. We know that you began the creation and you want us to pursue after you, Lord, so help us to understand how we can pursue after you today, Lord. Whether that's through our studies or through our devotional time with you, our quiet time with you, or if it's just spending some prayer time with you, Lord, that's much needed. Lord, we pray that you just ignite that fire in our hearts just to seek after you, because you told us if we seek after you, we will find you, Lord. So we just pray for that time with you, and we seek after your presence. Lord, we pray just for the people around us who don't know you as well as we do, and we just pray, Lord, that we can share you with them in whatever way that might be, Lord. We pray for all people to turn their eyes towards you, Lord. We just ask all this in your name. Amen. All right. So, we got that. We're good. 100%. Everybody understands everything there is about drawing things. Yes? Okay. All right. So, now that you guys know everything there is about drawing things, I'll do this, and then let's see. Today's a red type of day. Okay. So, I want you guys to draw that structure. Okay, I want you guys to draw that structure right there. Put in all the hydrogens. Is that going to work? Nope. Figure it out a little bit. Okay. And you're right-handed, I'm supposed to? Oh, yeah. So the top carbon? That one? Yeah, it would be out there. That's definitely, but be careful, there's not So not hydrogens, are carbons, right?
So where's the positive charge then?
Right here.
Why would that one be positive?
Because that's where it doesn't necessarily have to be there on that end.
No, it's absolutely there, that's what I drew. Right?
Yeah, that's, I put it there because that's what you drew.
Yeah, so how is that represented here? That's what I'm asking you.
By moving the carbon bonded to these 3 carbons and then 2 hydrogens down there.
Okay, so what's the formal charge on what you drew?
Positive 1.
Show me how you did that.
So carbon usually starts out at negative 4.
So it's not a 0, right? It's a neutral thing. It starts out with 4 valence electrons, I'll give you that.
And then 3 hydrogens. Just the 3
I'm
carbons.
asking you how you do formal charge, that's where the question's coming in, right? Don't forget to explicitly show your form. Okay.
Nothing. Wow, man. Okay, I'm gonna ask the obvious question. What's the positive mean?
It has fewer electrons than it needs to fill its shell.
Okay, that is true. I'm not disagreeing with Andy on that. What does the positive mean, though? What is the positive? It is a formal charge, and formal charges are a formality, and they are for us to say, hey, there's something going on here, right? Do you guys need to know how to calculate formal charges? Should you get comfortable doing it just on the fly without thinking about it? Maybe, right? Be careful when you stop thinking about things. That's when accidents happen, right? Now, if I have a positive formal charge, that means I have access to less electrons than I normally do. Maybe, sort of, kind of, right? Okay. You guys with me on that? Look, this is the easy stuff. You guys want harder questions? If I have a positive formal charge, I have access to less electrons. Yes? Yes. Okay. Right? If I have a negative charge, that usually means I have access to more electrons. Yes? Yes. Okay. So the question comes down to, well, how do I give a carbon a positive formal charge? Right? We'll have to take things away from it. And just for simplicity's sake, right? Let me just get rid of that since I kind of drew myself into a corner here. Okay, got that, we got that, we got that, right? I think everybody, I'm not going to draw in all my hydrogens there. You guys can kind of fill in the blank that the blues are the hydrogens. Sound fair? Everybody with me on this? Now, if I ask you guys to do the formal charge on that carbon right there, what is it? How do we do that? How do we approach it? So remember, this is where we take our magic science circle, yes? Science circle surrounds the atom we're looking at. Valence electrons, right? Minus what's in the circle, right? Gives us our formal charge. So we have 3 things in the circle. We start out with 4. 4 minus 3 is positive 1. So when you see a positive formal charge on a carbon, it means it's missing a bond, typically to a hydrogen. Does it always have to be a hydrogen? No, it does not. It's just missing a bond. For our purposes right now, at the beginning of the semester, we can assume it's missing a bond to a hydrogen, although we'll very quickly move away from that notion. Everybody with me on this? How do I give that carbon a negative charge then? What if I just go in here and do this instead? How does that change what's happening on that carbon?
You'd have to add more things bonded to it.
Maybe I have to give it more electrons, right? Yeah,
It could have a lone pair.
it could have a lone pair, okay? So if we're doing the same thing, let me just erase this here for clarity's sake. Right, if I put a lone pair there on that carbon, right, I've got my 3 electrons in red, right, from the 3 bonds, and I've got my 2, right, that are coming from the lone pair in black, right? 4 valence electrons minus the 5, right, makes a -1 charge. Everybody with me on this? Good? So when you see positives and negatives on carbons, this is what we're talking about. Well, I am going to present something to you. My thought is that I could easily accomplish a negative formal charge just by doing this, right? Is that a negative formal charge on that hydrogen?
Mm-hmm.
Yeah.
You're not wrong though, because carbon exclusively. falls
Wait,
under that rule.
I'm wrong?
Yes, sir.
Oh, please correct me. How could I be wrong?
Carbon exclusively follows the octet rule and only makes 4 bonds.
Got it? Everybody with me on that? That's important to recognize. Does that have a negative formal charge? Absolutely. Is it correct? No. Okay. So, for the purposes of our class, typically we'll be dealing with carbon in its 0 formal charge, right? That's going to be where we see most carbons. However, as we go through and do reactions, we're going to end up with intermediates. Intermediates is where we start to see charges on carbons, particularly positive charges, okay? So just going back to the previous example that we had, okay, if we go back to the previous example that we had, this is what's known as it's got a very difficult name to remember. Let me see if I can remember. I always forget what its origin is. Let's see, it's a carbocation. I forget how to pronounce it. I'm just kidding, right? It's a carbocation. You guys with me? It's a carbon that's got a positive charge. That's what it's called, okay? Good. This is going to be the bane of your existence, because I predict, whether you guys do or don't come to my office, right? You guys are going to get an exam or a quiz or something, and there's going to be a time where you miss a carbocation or you misuse it, all right? It's going to be a very, very, very important intermediate for us, okay? Sound good? Sound fair? I'm just warning you, okay? I'm giving you a vision of the future. Much like John in the desert, I'm screaming at the sand, right? Right? You guys with me on this? I'm telling you what's going to happen. We need to pay attention to this. Formal charges are a formality. I don't want you guys to miss this, okay? I want you guys to hear the message. But we have to be careful when we're dealing with carbocations, okay? Good? All right. Now, question. Oh, I guess I should go back for just a quick second here. If we put the negative charge there, although you guys can probably figure this out, this is called a carbanion. Carbanion. We'll be dealing with these quite a bit more, a little bit this semester, way more in the second semester, okay? Carbanions are actually not as common in terms of intermediates, although they are very common reactants, right? So they are things we can add into a reaction to make something happen, okay? Carbocations, not really that common as reagents themselves that you can that you can add in, but very common in terms of intermediates. So we'll get into more detail with that, okay? All right, so back to what we just had there. Let me draw my perfect hexagon. Okay, I want you guys to draw me all the resonance structures that are available for this molecule. And while you're doing that, I want you to show me the arrows that push the electrons around. So the arrow pushing mechanism, the electron pushing arrows, or the curved arrows as the book talks about it sometimes. Show me the movement of electrons, that's all I'm saying. I know I tend to fight years of habits sometimes in this class. One habit I can recommend to make life a little bit easier, although you won't believe me immediately, is draw bigger things. Don't be afraid to use paper. I will give you guys paper if you need it. Nice printer paper, okay? All you guys can, okay? Don't be shy is all I'm saying. Draw something bigger, it's easier to see things, right? A lot of people got their PhDs over the weekend. Skipping steps. How many resin structures are there for this? We got this one plus one more. That's it. Lots of you guys weren't paying attention because one of the, let's see, the mortal sins of organic chemistry. Okay? One of the mortal sins of organic chemistry is that you guys made bonds, 5 bonds to a carbon. Okay? Did you guys see that on your paper? You guys forgot the hydrogens, didn't you? Mm-hmm. What are we doing with a resonance structure? What's the only thing we can move? Electrons, right? Electrons that are either as a pi bond or as a lone pair. Got it? Can you move electrons to a carbon that already has 4 bonds? No. Right? You know what happens when you move electrons to a carbon with 4 bonds? You make pregnant carbons. Very irresponsible. Okay? You don't want to do that. But it's going to happen. So how do you avoid that, especially as we're starting to develop, okay, our skills drawing resonance structures? What is the best tool you guys can do when you're first developing your resonance structures to make sure that you don't over-octet a carbon? Don't give it more than 4 bonds. What should you do?
I would draw the loose structure.
Draw out all the hydrogens. Got it? Because then all you have to do is that has 4, can't move there, okay? That's it. What's that positive thing mean again there though? It's a formal charge. It has a positive, right? It's on a carbon, which means that carbon has less than 4. Can we move things there? Can we move things there? Yeah. Does it have 4 bonds to it? No. Is it missing electrons? Yes. What do we move again when we're doing resonance structures? Oh, I see.
Are you sure it's not neutrons that we move?
I am sure. Does everybody follow my logic with this here? I have a positive charge. It's missing electrons. What's attracted to positive charges? Negative things, electrons, got it? You guys with me? You guys following what I'm saying with this? So if you see a positive charge, we're missing electrons, we can probably move some electrons towards it. Do we have electrons next door that we can move to it? Yes, they're in a pi bond. Got it? So what we can do is this. And life is good, life is happy. Okay? I'm done. Time to give myself the old pat on the left shoulder there, huh?
There be a formal charge on the carbon from where you switch the bond.
Got it? Am I done? No, because you're skipping steps, right? So when you're thinking about this, right, let me go back and fill in the steps that I skipped here, right? There's a hydrogen here, two of them, two of them, two of them, right? And three of them there. You guys with me on this? So I don't move any hydrogens around, okay, when I'm drawing a resonance structure. Let me do, yeah, black seems reasonable, okay? So this black carbon right here, how many bonds does that have to it?
3.
3, is that less than 4?
Yeah.
So what charge would that carbon have?
Positive.
Positive, got it? Does that make sense? Why does that make sense? Outside of the whole counting from 3 to 4. What did I do to that carbon in black?
Nothing aside from breaking the bond.
I took electrons away from it. If I take electrons away from something, what usually gets left behind? Does that make sense? Is this a coincidence or is this logic?
Can't it be both?
I would say we are in a science, and science is based off of logic and observation, right? You guys with me on this? This is key. You have to know how to draw resonance structures. Have to. Have to. Yeah, what's up?
Do you mind explaining again why you moved the bond?
Why did I move it? In what sense?
Like why you moved it to the top?
I'm not trying to be nitpicky, I'm trying to understand your question.
Like,
So, why would this happen, or why did I ask you to do this? That's what I'm trying to. Why would this happen? Great question. Why would this happen? What did I say about formal charges? Remember we looked at carbonate. Okay? Where do atoms like to be in terms of their charge? Neutral. What happens if we give them a charge? They get hangry, right? You guys know what I mean? They're grumpy. What's the best way to get rid of a grumpy attitude? Spread it to somebody else, right? Just wreck their day too, right? Screw that guy. He stared at me weird, all right? I'm going to go right in. You guys with me on this? It's spreading the misery. The misery here is that there's something with a positive charge. But where is that positive charge? Is it only here? No, it's also here. Is that positive charge spread out? Yes, over both of those carbons. The more we can spread out a positive charge or a negative charge, you guys can fill in the blank, right? The more we can spread out any charge, the more stable that becomes. This is key. This is one of these key things. The more we can spread out a charge, the more stable it becomes. The more stable something is, now you guys aren't going to believe me, right? The more stable something is, the more it reacts. Ooh, that is key, okay? In your mind, you're like, well, the less stable, the more reactive, because you're thinking like in the psychological terms, right? That guy's unhinged, he's about to do something. That's not how, right? That's not how molecules work, okay? The more stable, the more reactive. And we'll talk about why that is and kind of clarify that statement. One of the key ways we have of stabilizing charge is through resonance. I'm going to give you guys 5 ways of stabilizing charges as soon as we get to chapter 3, okay? Maybe a little bit before that, if I just depending on how things go, right? But the number one is gonna be resonance. And so when I ask you, when we get to that part, hey, how do we stabilize charge? Your first answer is gonna be? Okay, and that's probably gonna be the best answer for most cases. From now, all the way through the end of biochemistry. And even beyond that, okay? When you guys are defending your thesis for your chemistry PhD, okay? And they ask you, how do you stabilize a charge? You're gonna say, I don't know anymore, okay? Right? It's gonna be resonance. Got it? Very important. So how do we represent resonance? Do you guys need to know how to draw them? Do you guys need to know how to push the arrows and all that kind of stuff? Absolutely. Yeah, what's up?
Resonance makes things more, sorry, what's the word? Makes things more stable. Is the implication there that the molecules are always moving around, the electrons are always bouncing from place to place like that?
Yep. Everybody with me? Are these equivalent resonance structures? AKA, are these the exact same? No, they are not. Does everybody see that? That's also important. We have equivalent and we have inequivalent resonance structures. Yeah.
Well, I don't know, you may have already explained this, but I don't understand how there is like still two, or single hydrogen after you move the double bond. Like, I don't know how they can stay just.
So part of a resonance structure is we can only move electrons, not atoms. If I move atoms, I'm doing some kind of reaction. I'm rearranging the molecule. Right? So this is why I'm telling you one of the best ways to learn how to draw resonance structures is like explicitly draw your hydrogens. And if you end up moving any of those, you know you did something wrong. The only thing you can end up moving are pi bonds or lone pairs. That's it. Okay?
Is that why you moved the, positive?
I didn't move I'm not picking on you, I promise, but this is an important point. Did I move the positive? No, what did I move? The electrons. As a consequence, the positive moved. What's the only thing that does chemistry? Electrons. Got it? One of the common mistakes is that I see something like this drawn. Okay? Is that how this works? A positive charge on a carbon for us is an empty hole. Can you move a hole? Well, you cut around it and you pick it up. No, right? You can't move a hole. You got to fill it in and then dig a new one. You guys with me on this? Don't move a positive. You can only move negatives. The consequence is that the positive moves. All right? Cool. Let's do more. Gonna really change things up. You ready? Okay, show me all the resonance structures. So remember, as we're learning, what's a good tool to do? Draw out all the stuff that's implied, right? So not only hydrogens, but what else is implied? Lone pairs. Aha. Can we move lone pairs? Yes, we can. That's your ambidextrous now, right? Good thing you got Jill sitting next to you, right? I'm sure she'd be more than willing to share notes with you.
Yes.
arrow here doesn't represent what you have drawn here. You left off a lone pair if you're doing that. Right, if you're saying the lone pair turns into that bond, make sure the arrow comes from here to this. Okay. So draw what that product is gonna look like there, what that structure is gonna look like. So you got 5 bonds of that carbon right now. That's okay. So go back to what I was telling you there, right? So everything happens because of the electrons. If you see a positive, it's an absence of electrons. So try and move electrons towards it, right? Be careful here. How'd you get that positive? There. Well, how'd you get it from here to there?
The electrons move from this bond here.
So if you're trying to do that, then show me here, right? Because if you draw that arrow here,
Okay.
right?
So I draw the arrow here.
Right, now show me that product that you have
Oh, I
specifically,
see.
right? Don't put the cart in front of the, or the cart in front of the horse, so to speak, right?
That makes sense.
Is this next door? No, so can that happen? Probably not. In fact, I'll go and answer that, definitely not. Except when it does, but that's outside the scope of this class, so. Good. So now, again, here we have a positive charge. Do you have anything we can give to it? Perfect. So here we got our positive. And we have an absence of electrons. Can we give? There you go. See how easy this is? Find something negative, find something positive, right? Why does it take 2 semesters for it? Be careful. Draw your arrows in, and your positive charge isn't going to be there, right? So you got rid of too much stuff here. Right? So think of it, right? The saying goes, you're eating an elephant, right? How do you eat an elephant? One bite at a time, right? So do one step at a time.
Because then this carbon is gonna fly things.
So be careful.
Oh, maybe the back here like this.
Sorry, so that should be a positive. We'll go through to the negative one just a minute. All right, this is why I keep telling you, right? How does all of these here for you? Negative.
Oh, I see.
Positive. There's very positive.
Like,
Yeah.
it's
Some electrons.
Yeah, I think I should have messed
We
it
have to be fine on this.
It was fun doing school.
You're missing a line. Yep, in fact, that's. Right? What's unusual about it? Yeah, right? But remember, what do we say about flying stories? In reality, we're supposed to say, hey, wait, something is unique. What does it matter? Do you think that ours is the positive in reality? Okay, I like this.
It has to have
The arrows
details,
look
not
good.
just
It
details.
does electrons, right? Remember, you're gonna make, so you have one set, draw that first. Okay, then once you draw that, then come back. So put those as 2 separate. That's
I only know there's 2.
Okay.
Oh.
How can you make it one way?
Is there a way
And plus you're gonna find that.
I mean, one.
Okay.
like move? Is there a way to get the double bond down here?
So that's what it became like both.
What if you move the double bond and the pair and swap?
Can you swap things and move 2 things? Why not?
So the optional
It makes sense that it could be.
I'm gonna do that, I think I'm gonna do that. You know, be up top.
All right. Looks like we're on the right track here. So I realize my scribbles in the back might be a little bit difficult to see, so I apologize for that.
Double bond.
So that was a positive charge. We'll come back into the negative one in just a minute, right? A positive charge, help. What can I do? Move electrons around, right? That's always the answer, okay? I mean, you all know Jesus is always the answer, right? But resonance in this case too, okay? All right? I see a positive charge. Anytime you guys see a charge, your thoughts should be, hey, I need to see if I can spread that out. I need to stabilize that, is how we would say it scientifically, right? What's the only way I can spread out a charge that we know of so far?
Move some electrons.
Give it to another round.
Resonance. Got it? Resonance. What do we do when we draw resonance structures? We move electrons, and they have to be next door, either in lone pairs or
Double, triple.
pi bonds. Got it? Why do I keep saying the same thing over and over and over again?
Because it's important.
Because I gotta fill time. I've got 70 minutes to kill here, huh? Right? No. I say the same thing because guess what goes through my mind every time I do this? The exact mantra that I tell you. Got it? That's it. There is no Gnostic wisdom I'm holding from you guys here, okay? This is just the way that we do it. I see a positive charge. Okay, I look next door. Okay. Good. Good. Everybody got that? Very similar to what we did on the last example. Okay. Now what? Do I still have a positive charge? Yep. Okay. I look next door. What do we see? Lone pairs. What can we move when we're doing resonance? Lone pairs and pi bonds. Okay. Good.
What's the blue line?
Pi bond.
I'm done.
What's up?
Not there's a hydrogen on that carbon.
Yeah, there is.
Oh, it is making protons.
So the lone pair doesn't have to be a lone pair to the carbon. It can form a unhybridized bond.
Lone pairs can turn into pi bonds. Pi bonds can turn into lone pairs. Pi bonds can also turn into other pi bonds. Got it? Here we take a pi bond and we turn it into a pi bond. Here we take a lone pair and turn it into a pi bond. Got it? Can you guys draw me the arrows to go from here to here? Remember, all resonance structures should be related. So draw the arrows from this one to that one.
Since resonance is all about spreading the charge, would there be any point in, say, swapping the double bond for a lone pair?
No, because what happens when you do that? Well, let me back up here. There is an application of that line of thought in the second semester. We can use it as kind of a tool to predict what will happen, but that doesn't actually, let's say, happen in reality.
It's not a practical resonance.
Correct. Because why? What happens? So draw that out real quick. Draw what you're thinking, and you'll see why that's probably not a good move, right?
Okay.
It's a good thought, though. It's a good thought. me just switch here. Alright, you guys with me? Pi bond has to move here, blue has to turn back into a lone pair. Does everybody see what these arrows represent? Might take a little bit of looking at or thinking about here. Pi bond moves to here, which moves this pi bond back into a lone pair on the oxygen there. Yeah.
Are there not 4 resonance structures? Because you could take the one lone pair and, oh wait, never mind, you can't because there's 2 hydrogens attached to that carbon.
Okay. Drawing in your hydrogens, very, very, very useful at the beginning, okay? Which one of these is the best resonance structure? Which one would we expect to see predominantly? Ooh, good question, Dr. H. I know, thank you. Yeah?
Well, you wouldn't really see the third one as much because there's a positive charge on the oxygen, which is kind of weird.
Okay, that's certainly a good observation, right? What's the difference between 1 and 2? The positive charges on both on carbons, right? Now, what we're going to learn in just a little bit is those are actually different carbons. Well, the term I use are flavors, okay? One's a tertiary carbon, one's a secondary carbon. There is a difference between those. The actual answer is number 3, though. Darn it! Stupid science, you lie to me all the time, right? What's unusual about number 3? Go ahead.
The oxygen has a positive charge.
That's unusual, isn't it? How many times have you guys seen that? Almost every day. Oh. In fact, it's super duper duper important. Okay, you guys want me to prove it to you? Like, no thanks, my worldview is good. What's this? That's hydronium. Is hydronium important?
Yeah.
Yeah, that's what happens when you put an acid into water. Do you guys use acids in water every day? I hope you do, because how does your stomach work? It's basically hydrochloric acid, right? What formal charge does the oxygen have in hydronium?
Positive.
So is a positive charge on oxygen all that unusual?
No.
Yes, it is. Okay, but remember, how confused are you guys now? You guys get the point that I'm making, though. Here's the point that I'm making. Do we see positives on oxygens? Yes. We will actually see it quite a bit. What does that positive charge represent? It's a
Area of few electrons.
formal charge. And formal charges are a formality for us to say, hey, wait a minute, something is going on here. Got it? Here's the difference. Is this oxygen actually feeling positive? No, it is not. What do we know about oxygen?
Likes electrons. Good at attracting.
It's the second most electronegative atom on the periodic table. Does that change? No. Is it drawing electrons towards itself here? Yeah. Is it drawing electrons here? Yeah. Is it drawing electrons here? Yeah. Is that oxygen actually feeling positive? No, it's not. Does it have a positive formal charge indicating something unusual is happening?
Yeah.
Yes. Got it? Everybody with me? This is a key thing. We're going to see a lot of positive charges on oxygen. And for you, it should say, this is something unusual. I need to deal with it in some way. Hang on just a second real quick. But we still didn't answer my question, did we? Because I asked what? Which one's the most stable? And then your question back should be, why? One of the 5 good questions to always ask. Who, what, when, where, and why, right? Why?
Although you probably don't need to ask who here.
What's up?
So with resident structures and line push, arrow pushing, I
Yep.
just realized I'm doing it wrong. So when you say draw the resident structures of that with no
Mhm.
arrows on it, is the first resident structure to, like the line, if I put the double bond up to the left there, and I put the arrow, I'm sorry, I just,
Let me answer your question.
mhm.
Any one of those is valid, because all resonance structures have to be related. So I don't care which way you start.
But the head of the arrow should be pointing to where it's going.
Where the electrons go, yes.
Okay, I don't say I got it from here, now it exists here.
No, no, no.
Okay,
From where the electrons begin, they begin in the bond and they end in between here is what it is.
okay,
Yeah,
okay. So
Yes.
where it's going, not where it came from.
correct.
Okay.
And you should draw all three steps.
Yes.
Okay.
Yeah, these are all unique and good resonance structures.
Can you draw them separately, like if I went from 1 to 2 in one, and then from 1 to 3 in another?
Yeah, that's fine.
Okay.
Like I said, all resonance structures have to be related,
Yeah, okay.
right? Yeah. So why is this the best resonance structure? The answer is, a short answer is, everything has an octet. Got it? Whenever you see a positive charge on a carbon, right, it doesn't have a complete octet. I think the way the book describes it is, and it's a fair description, there are more bonds present. Everybody see what the book's talking about when they say this? We have 1 pi bond, 2 pi bonds here, right? So the more bonds we make, the more stable things tend to be. Remember, making bonds releases energy. Breaking bonds takes up energy. Now what's interesting, or at least I find it interesting, these structures with a positive charge on an oxygen are actually very, very common. So purple and blue colors in nature come from these things called anthocyanins, right? And they're these really, really cool looking structures, but they all have a positive charge on an oxygen, right? Very, very unique. When I first kind of started learning about these or reading up about them, it's pretty unusual. But you eat a blueberry, you're taking in anthocyanins, right? They're present in beets, right? The reddish, purplish color in beets come from that, right? So it's actually a very common structural motif that we see in nature itself, okay? But pretty unusual, but not unexpected is the point that I'm saying. Whenever you see a positive on oxygen, we always need to pay attention to it and ask the question, does it make sense in this context, right? That's what we say with hydronium, that's what we say with resonance structures with a positive charge. Sound good? All right, you guys ready for something completely different? It's gonna be way different. You guys don't believe me.
I have a quick question.
Oh yeah, what's up?
So in terms of lone pairs, on the first one you didn't draw the lone pairs in the oxygen. Do you not need to always indicate the lone pairs unless you're moving them?
So that's a fair point, right? So I typically, when I draw them in when I'm about to use them is what it is. If I were you guys, I would be drawing them in all the time. And feel free to ask me to put them in and I will. I just forget about it sometimes is what it is. But whenever you're using the lone pairs, absolutely draw them in. Good question. All right, something completely different, yeah? Okay, well, not completely different, it's still a resonance structure. Okay, draw me the resonance structures for this completely different molecule. Don't skip steps. hydrogens, right? You guys feel stuck? Go back and take a look at the resonance structures we drew for carbonate, right? I think we drew it for carbonate and nitrate, I believe. I don't want to judge harshly. How many electrons do you have here? Your arrows aren't no, that's fine, that's not what I'm meaning about. Your arrows aren't matching what you drew here though. I think that's where the issue's coming in. So draw up what your arrows are showing and then we'll see. The issue. Okay, fair enough.
We're still working on that part.
That's okay. The amazing part is we're not on the exam, right?
Cannot express the amount of videos about arrow pushing that I watched.
Good.
I still don't.
I mean, you don't instantly grasp something you just learned for the first time.
It's not instant. I watched videos all weekend.
How could I draw a resonance structure here?
Move the pi bond around between the three oxygens.
How would I represent that with arrows, though? Where would I start my arrows? This is part of what I say when you guys are fighting me all the time. I know it's not on purpose. It's not, it's not antagonistic. How does all chemistry work? Something negative, right? So, just like arguably the most important sentence in the Bible is Genesis 1:1, right? In the beginning, something negative. So where should I always start to look?
The electrons?
At the negative. Got it? Okay, so I'm going to move my negative. Good. What did we accomplish in right? What did we accomplish in this resonance structure? How did we do it? We started from the lone pair and we pushed up a pi bond. Can you do the exact same thing over there?
Yes.
Yes, you can. So do it.
All your negative. It's an interesting thought. Draw that out, and then you might see what could happen with it, right? I'm talking about the negative, right? There's only one negative on that structure. Yeah, yep, yep. I hear it all churning. A little bit too much. I like, remember starting from the negative from where you're, right? So your arrows are pointing towards the negative. That's very rarely, if ever, gonna happen, right? Arrows should always be going away from the negative. Because what you're telling me is electrons are going towards something negative. That's not really gonna happen. Good. Don't forget your charge. One more more. Okay. It started here. What happened here? What did those turn into? Okay. Would it be any different here? Probably not, right? Ah, perfection. I have solved the mystery. Does that arrow make sense? Why or why not?
There's 5 things in the carbon.
Because electrons don't attract electrons.
Good, so for both those reasons, right? If I follow my red arrow, I will over-octet my carbon, and what I'm saying is, hey, I've got a carbon that's negative, I'm gonna send more electrons to it. Does that make sense? No. Arrows always start from the negative, and they go to something else. Got it? So not that red arrow. All right, Dr. H, I got it figured out now. Let me just draw this in here. Remember, just like what I said with drawing in your hydrogens is going to help you guys figure this out. If you've got a negative charge, draw in your lone pairs. Where should you guys start looking for things to move around? Well, if you see a negative charge, start there. Got it? Okay. Good. Everybody following what's happening here? What happens though, right? Follow with me here for a second. What happens if I just have that one arrow?
You're gonna end up overcharging the one carbon.
Okay. I would end up putting 5 bonds to that carbon there. Why? Because I've got that hydrogen right here. Don't forget about it, right? Did you guys draw in your hydrogens? Some of you guys didn't. You're like, man, Dr. H told me to do it, but I think he's talking to the person in front of me. Okay? I'm telling you how not to miss these problems. just draw them in. Okay? Because if I follow this along here, yeah, here it is. Right? If I do this, right? I hope that would be a little bit more obvious now that something not good is happening there, okay? I don't want you guys to do this on an exam, but it's one of the most common things that happen. You guys forget to fill in your hydrogens or whatever it is, and then you guys just send pi bonds off to somewhere. And you commit one of the mortal sins of organic chemistry, right? 5 bonds to a carbon. Don't do that. So, let's learn another mantra then. One of the other mantras that you'll end up seeing me kind of chanting over and over again as you go through things is that if we make a bond, we should break a bond, okay? So is that always gonna be the case? No, take a look at the previous resonance structures we did, okay? But as we start to move negative things around, we'll start to see this come in a little bit more, okay? So when we're moving negative things around in a resonance structure, we make a bond and we need to break that bond right there. So what happens to that bond right there? Okay, got it. But that's gonna look just like the other one, Dr. H. I like that other one, it was nice. Is this the same molecule that I had before? No, it is not. It's a key thing to recognize. It looks very similar, doesn't it? Is it behaving very differently with its resonance structures?
Yeah.
Okay. Why can you not draw that arrow in blue? What would happen?
You, overload both the carbon and the oxygen.
Not overload the carbon, but overload the oxygen. Everybody with me on that?
Yes.
Okay? You gotta have a hole, you gotta have space to fit the electrons. That oxygen does not have the space to do it. So what can we do instead? Well, I'm gonna take that pi bond, and I'll pop them up to there. You guys with me on this? So let me follow around these arrows here now. I know I've been kind of hopping back and forth. I make that bond in red. What does my blue arrow turn into?
A lone pair.
Lone pair, right? Good?
I'll be darned.
Is there anything wrong with what I did? Well, the lines aren't symmetric. I left a little gap here and there, right? Everybody follow along with this. For some reason, I'm just telling you, a lot of the way I start to teach, the older I get, is I keep seeing patterns that you guys miss over and over and over. And one of the most missed things on exams is that you guys can very easily start to draw these resonance structures with positive charges. As soon as I throw a negative in there, you guys are like, whoa, okay? But you guys know how to draw these. This is what you were doing all the way through Gen Chem. Nitrate and carbonate, all those are just moving negative charges around. It's not any different here, it just looks different. And when something looks different, we need to be able to practice it. So you've got to practice resonance structures. Got it. There's a fantastic whole chapter in, whole section of a chapter in chapter 2 there about resonance structures. Work through the problems. Practice it. Okay? All right. I'll see you guys on Wednesday.